Heat kills humans in exactly four ways, and understanding these mechanisms explains why emergency sleeping bags work so effectively compared to traditional insulation methods. Today, I'm breaking down the physics of thermal regulation and showing you why space age materials outperform everything else. Heat transfer occurs through conduction, convection, radiation, and evaporation. Emergency sleeping bags address all four mechanisms simultaneously, while traditional camping gear typically addresses only one or two mechanisms effectively. Conduction happens when your body touches cold surfaces like ground, rocks, or metal. Traditional sleeping bags provide some conductive insulation, but emergency sleeping bags create complete barriers between your body and cold surfaces. Convection occurs when moving air carries heat away from your body. Wind chill demonstrates convective cooling. The same temperature feels much colder when air moves across your skin. Emergency sleeping bags eliminate convection by creating sealed environments. Radiation represents the most significant heat loss mechanism in most survival situations. Your body constantly radiates thermal energy into the environment, and this radiated heat is lost forever unless reflected back. Emergency sleeping bags excel at radiation control. The reflective surface of emergency sleeping bags bounces thermal radiation back to your body instead of allowing it to escape into the environment. This creates a positive feedback loop where your own body heat accumulates around you. Evaporation causes heat loss when moisture changes from liquid to gas, taking thermal energy with it. Sweating cools you through evaporation, but so does moisture from breathing, wet clothing, and environmental humidity. Emergency sleeping bags control evaporation by creating vapor barriers that prevent moisture from carrying heat away from your body. This is why they work even when you're soaked from rain or snow. The physics of emergency sleeping bags explains why they work better when you're already cold. Traditional insulation requires your body to generate heat, but reflective materials work with whatever heat your body produces. Thermal dynamics in enclosed spaces follow predictable patterns. Emergency sleeping bags create small enclosed spaces where reflected heat accumulates quickly, while traditional shelters create larger spaces that require more energy to heat effectively. Material science determines thermal performance characteristics. The metallized films used in emergency sleeping bags reflect over 90% of thermal radiation, while traditional materials absorb and re radiate heat instead of reflecting it back. Surface area calculations show why emergency sleeping bags work efficiently. By creating close fitting enclosures, they minimize the space your body heat must warm while maximizing the reflective surface area that returns heat to you. Air gap thickness affects thermal performance in complex ways. Emergency sleeping bags optimize air gaps for maximum thermal retention while maintaining flexibility and packability, a balance that requires precise engineering. The physics explains why emergency sleeping bags work equally well in different climates. They respond to your body's thermal output rather than environmental conditions, making them effective in desert cold, Arctic conditions, or temperate weather emergencies. Understanding the physics helps users optimize emergency sleeping bag performance. Proper deployment techniques maximize thermal reflection while minimizing heat loss through gaps or poor positioning.